So, welcome back to Entangled Discussions. I must say it's great to be back after our summer hiatus. It's great to see so many familiar faces and so many new ones too. So, for those who haven't been with us before, we're a friendly, inclusive group, and we encourage interaction. So please use the chat box for any questions along the way. And for those comfortable to take the mic, there'll be an opportunity to join in the conversation later on in the event. These talks are recorded and go onto our Entangled Discussions YouTube channel and will be shared on LinkedIn. So without further ado, it gives me such great pleasure to introduce today's guests. He's also an old friend of the show, and when we were scheduling the roster for this series, back with a big bang, how Quantum 2.0 interacts with space, it was inconceivable we could have this talk without inviting Rupesh Srivastava to join us. And thankfully, he was gracious enough to accept, and he's here today to talk with us about the Quantum Pathfinder Challenge, so amongst other things. So for those of you who know Rupesh, you know what a treat we're in for. For those who don't, sit back and enjoy. Welcome, Rupesh.
Thank you, John. Thank you for inviting me, and hello to everyone who is either preparing, I can see from the chat comments, breakfast, lunch, or dinner. So hello, everyone from Argentina.
So, Rupesh, I suppose let's start with a nice, easy one to begin with. Why is space an important sector for quantum?
It's a wonderful question, and for me, it's an absolutely natural mix. And that mix really comes from not just from the science, which I'll talk about in a second, but it's actually from my childhood. So I grew up with Star Trek. I grew up with this idea of people coming from all over the world and from other planets, working together, a voyage of discovery, discovering the mysteries of the universe and physically getting there. And that was the key thing. Until recently, until very recently, and alas, I'm not rich enough, but one day, space tourism is going to kick off. We've just had Captain Kirk blast off into space, William Shatner, at the age of 90, and that's completely inconceivable.
True.
So when we're talking about the human expansion into space, we're also talking about our beloved planet Earth, how we live more sustainably, how we address the challenges facing us, and how technology innovation can take us further, working together, creating new industries, creating new services, helping humanity in lots and lots of different ways. And that is what is really exciting about the what we term the Quantum Pathfinder Challenge.
And moving on to the Quantum Pathfinder Challenge, what is it? What's your view for it? What's your view of it? And how did it come about?
Well, this is the extraordinary thing, because so this is in the UK program, the UK National Quantum Technologies Program, and this is before the Airbus Challenge. This is before the BMW Challenge. These challenges are starting to becoming more commonplace as quantum technologies take off. But you have to remember, this is at a time when people didn't really know if quantum computers were ever going to happen, let alone engaging sectors together. So being based at Oxford University in the physics department and having the Harwell campus nearby and engaging with various colleagues. So in the Harwell campus, there's a space sector there, about 90 organizations or so, maybe more now. And the European Space Agency is there, the Satellite Applications Catapult is there. And I was talking to a colleague of mine called Simon Jackman. He's a fantastic, fantastic guy. And we were talking about quantum and its potential. And he was talking about space, which is far more advanced, okay? And he was talking about various ideas about disaster, monitoring disasters, monitoring agriculture for using satellite data, and how close was quantum computing, especially to addressing these challenges. The problem with the space community, or Earth observation data in particular, is that there's petabytes of it. There's too much and you can't handle it. And it's getting worse every single year, because as you have more satellites going up, they're smaller, they have more capabilities, high definition video, for example. You have so much data. Yep, as somebody said, debris as well. There's so much data. What do you do with it? Apart from storing it and hoping you could deal with it at some point. So we started to think about addressing key challenges. So the space industry, the UK space industry, just for those who are not familiar with it, you can roughly divide it into four categories. So one is manufacturing, which is space equipment and subsystems. Another is operations, so that's launches, operation of spacecraft and satellites. Another is support services. They're wide-ranging. And another, and a really important key one, is applications and services, which includes, the most famous is GPS, but it includes all kinds of things. So the question becomes, how can quantum computers, which are really early, so this is back in 2017, early 2017, we started talking, and we decided to do something about it in a series of events which kicked off in 2018. But the key question is how do you bring two communities together? A space community which is way more advanced, which is doing lots of different things across those four areas that I talked about. Space tourism was being discussed, policies being discussed at government level, how to enable that, and various sites around the UK were being positioned for launches. So it was all very exciting. It was all very new. There was this feeling. I'm trying to convey this feeling of excitement, of frontier, uncharted frontier work, which is why I go back to Star Trek again. And you can then broadly define, if you're going to talk about satellite operations, you've got a kind of upstream, which is putting stuff into space, and downstream, which is essentially data. What do you do with the results coming down? So we decided to put all this together under one umbrella. And the first challenge was to get started. Can we create a quantum space ecosystem? Can we start to address the key challenges that the space industry faces in the years to come as quantum computing becomes more powerful? Can we develop the know-how? Can we build the relationships? Can we bring quantum readiness to chief executives, to MDs in the space sector in the UK? That's a quantum Pathfinder challenge in a kind of a microcosm, a nutshell.
Yeah, so how to start unpicking that? So obviously there's a lot of different aspects that go into this, a lot of different players, but were there any sort of particularly interesting stories along the way that occurred?
Well, what can I tell you? Yeah, of course. So one of the having convinced different players that the time was ripe and it was ready now to talk about quantum and gain their support. And by support, I mean the European Space Agency. I mean the Satellite Applications Catapult, to help to convene industry. The first issue we had was a communication issue, believe it or not, because each sector has the most, each sector has their own jargon, their own vocabulary, and their own perceptions. So what we decided to do was what we wanted to do was to get to use cases, so business use cases. So what we decided to do was to organize an event with industry and have a communicate and have the morning spent in communication. So the space industry talks about their challenges, what they worry about on a day-to-day basis. And the quantum community talks about what they're up to. And facilitated by experts from both sides. And it was absolutely clear from the get-go. And I remember standing in the hallway. We had 50 organizations from the space community attending. And it was very clear we weren't on the same page when it came to language. We weren't on the same page when it came to expectations. And we thought about the event very hard, and that Galileo 5 video, that's how we kicked it off. We did not kick it off with quantum, and I was super clear about that. I said we introduced quantum and we start talking about quantum, of course, but we are space focused, and we're in the business of space. We're bringing quantum to space. We're not bringing space to quantum, if you get what I mean. And so I wanted it to be an inspirational and aspirational thing, and that was a perfect video to kick it all off. Yeah, and of course, the comments we got. What was funny about that, John, was the comments we got were saying, "I must watch The West Wing again."
Well, hopefully we can get some sort of commission from them when everyone else starts watching it again. So obviously, speaking of the West Wing, so the Quantum Pathfinder Challenge has a UK focus. A lot of what we see when it comes to space comes from over the pond. So was there sort of much interaction with NASA, for example, or
well, okay, the NASA interaction actually came later. So the Quantum Pathfinder Challenge was actually a series of about 4 events, which took place over 12 to 15 months or so. But the interaction with NASA happened at a fundamental physics workshop. So I was attending that in DC, in Washington DC, in 2019, and representing the UK quantum program there. And so my role was to discuss what we were doing in the UK in quantum technologies as a whole, and how we were applying that to space, which is pretty early on. As far as NASA and JPL were concerned, it was trying to get to a US strategy around quantum for space and how important it was. And you may know, and the viewers may well know, there is a cold atom laboratory in space already, and the International Space Station, and that's going to be upgraded in the next few years. So you're going to have more sophisticated Bose-Einstein condensates laboratory in space. So the question then becomes, what do you do? What other technologies could you put up there? So back to the Pathfinder Challenge, when we talk into this UK Space Agency, they said, what do you want to do? Do you want to put a quantum computer up in space? And then they laughed. And at that time, it was more usage of quantum computers in particular use cases, rather than actually putting up a a computer. But you know, over 5 years later, well, why not? Especially in advances in photonic quantum computers, you can start to see things being shrunk down, semiconductor fabrications happening. So you can start to see, what if we had these entangled resources up in space, plus compute power? And in my talk that I gave at NASA, I showed I showed a picture of a ship. And what I mean by ship is, got to clarify, it's a one of these tall ships, a sailing ship, the old-fashioned kind that required wind power. And I asked them, and I asked the audience, NASA engineers and scientists and delegates from around the world, if they recognized what that ship was. And there was silence. So I said, okay, I'll give you a clue. It's the HMS Beagle. And then one of the NASA engineers, senior NASA engineers, said, Charles Darwin. That's the ship that took Charles Darwin to Australia and other places. And people were intrigued as to why I was showing this picture, this really old-fashioned historical image, in something in a workshop, which is in a conference which is cutting edge. And the reason is really simple, because we tend to forget why we're doing things, because we're so focused on either the cool science or the cool technology, and it's and the really important applications of that, which includes economic benefit to a lot of people. We forget about the people. So I said, imagine this: Charles Darwin's a young man. He's on this voyage where anything could happen. There's no GPS. There isn't a telephone call to bring out a helicopter or ships if they're attacked by pirates, or if the ship capsizes in a storm. So the risk is way up. I mean, it's astronomical, the risk, right? But yeah, he goes. And with that, eventually comes the theory of evolution. But what if the ship had sunk, is the question I asked them at the time. So the point is, when we're talking about risk, it's different when you're talking to entrepreneurs who are natural risk takers. But when you're talking to people who aren't, then it's a problem. And it's to convince people that it's really important to take risks. It's really important to try things, and to also expand laterally in your thinking. So, for example, if you have an entangled resource in space, and say entangled with a ground station, of course you can do QKD type experiments or whatever, quantum comms, as it becomes more sophisticated. However, why not use it as an educational resource as well? Why don't you have a web-enabled interface that allows school children to start to explore different types of quantum experiments? And it's super cool because, you know, you're over 1,000 kilometers up or whatever. And so they can do quantum teleportation experiments, entanglement, start to see how the fundamental laws of physics work. And if you have those as CubeSats, it needn't be expensive. And so if you choose their orbits, for example, if they're in geostationary orbits, then you can start to cover the world. How cool would that be? Because then you could also document how those were created, how the systems were programmed, what kinds of people and talent it took to create all of that in order to learn and then create in the future the next generation of space engineers, scientists, quantum workforce, whatever you want to call it.
Yeah, I think the risk-taking aspect is something that's always fascinating, because through, and coming back to the Charles Darwin comments, through natural selection, certain risk takers get an advantage due to the risk they take. Other risk takers are no longer in the gene pool due to the risk they take. And then those that sort of stick with the safe, secure model tend to not to sort of be in between. They're still in the gene pool, but they don't maybe have the advantages acquired by whatever that risk was. And I've seen people talk about creating fire and things like that in the chat. So it seems that risk taking is quite different in modern times, or certainly within, for example, the UK, North America, the sort of Western civilization. What constitutes risk taking is different to what it was, 1,000 years ago, even 100 years ago. That sense of risk is very different to what it is.
That's right. Just in quantum computing, just globally, just a general comment. You see countries like Japan just willing to try stuff earlier.
Yeah.
And I love that enthusiasm and the optimism. So when we're coming back to space, what I want to absolutely make clear, this isn't sort of, with the Quantum Pathfinder Challenge, we were getting going. This had not been done before. So, you have a communication issue, people speaking different language, using different jargon. You have a risk issue. I had raised eyebrows when I talked about the using entangled resources up in space for educational purposes. Okay, so maximizing the use of those resources. For me, it was an obvious thing to do, but it wasn't so obvious to anyone else. But it was also applying very specific categories. So, for example, optimization problems. So, comments made by a NASA official was, how do we optimize a Mars mission? So when you start to think about that, and ultimately you want to end up with a base on Mars, you have to have some kind of sustainable way of living. So and a whole range of different technologies like 3D printing or whatever else. But when you're talking about optimizing, you're talking about logistics, you're talking about scheduling, you're talking about improving manufacturing processes, you're talking about how you manage complex supply chains, navigation of whatever you're putting up there. And these days it's constellations of satellites. And navigating those, would it surprise you to learn it's still being done through spreadsheets in some cases, or in quite a lot of cases. It's just getting exponentially difficult. If you've got debris, space debris is, lots of people know about that too. And that is a huge problem. Because now it's not just about how you manage the space debris and get rid of it, but how you mitigate against it. So how do you choose your orbital pathways? And you've had near misses, and there are more of them happening all the time. But also it's about the resources that are already up there, that you've spent billions, hundreds of millions getting up there, and maximizing those. So for example, communication tech. Could you make more of existing platforms? So here's another one. Space, I don't need to tell anyone that space is a really harsh environment, right? In terms of temperature extremes, in terms of radiation, and it varies by distance, depending on the orbits that you have. So you need new materials. You need space-grade materials. And finding new materials, as everyone knows, is quite difficult. It's something that quantum computers could help with, along with AI. But then you need somewhere to test these materials and get them approved. And you need to then accelerate that process. Okay, so how do you make quantum tech space ready quicker? So you need a dedicated center that can do that with all the test equipment that is needed. What about chemical and biological processes? And they change in microgravity compared to here. And they change in, of course, when it depends on your radiation shielding, of course, but it depends what the environment looks like. And that could be harmful for humanity or could actually be very helpful. So already you have on a small scale, crystals being grown, biological processes being evaluated. But what if you had a more sustainable space? So you improved solar panels so they're far more efficient, lasted longer. The impact, were more resistant to impacts from radiation, for example. Better batteries. Things that can help down here, but also help up there. So, it's a win-win. And to do all of this, you need to speed things up. You need new engineering tools. You need innovation. You need improvements in, for example, fluid dynamics, computational fluid dynamics, Monte Carlo simulations, finite element modeling, all of these things that are used day to day. But we need to turbocharge them. We need to get really better. And then if we're just sticking with the Earth for now, and I'm eager to move on from here, but then you have Earth observation data. And then you get into a situation. So Earth observation data could be related to agriculture and food security, for example. Water management is a hugely important topic. It's important for humanity because the next wars could be fought over water, for instance. Disaster resilience. We're all, I don't know about you, but it's sort of, I don't know how people feel. Are you becoming more desensitized to hurricanes and tornadoes? But this is a huge problem for the insurance industry, because suddenly when you have a picture, before and after, how much exposure does the insurance industry have? Are they able to tell on the before picture what assets were there before they were wiped out? And then they can then be informed about how much exposure they have. So we talked about water, but what about land erosion? What about scenario analysis? So one of the things here in Mendoza, I just want to give you a fun fact, is it's a desert region. And because of the ancient technologies of the indigenous people who used sort of small canal-like ways of moving water around, it will surprise you to learn just how green parts of Mendoza are. But the question is for the planners, for the city planners, where do you put new developments? How much water will they consume? What's the best way of doing it? Where would you plan the new roads? So you need these kind of what-if scenarios. The amount of variables is really complex. Bear in mind it's an earthquake zone as well, and you've got a real headache. Can quantum computers eventually help with all of these things? Another use case for Earth observation data. So you've got an image, and you've got some clouds, you've got the ocean, and there's a dot, a bright dot in that picture. Is it a ship? Is that ship lost? Because the transponder is being switched off. Is it a smuggler? What is it? And to start to understand our world, you need to be able to make sense of the data. However, there's all kinds of data. There's radar data. There's gravimetric measurements. So quantum technology is up in space measuring the changes in gravity around the world. This data is not standardized. So this is a problem. So some kinds of data, and depending on the angle that the satellite is, you get a projection of that data too. So it gets smeared out a bit, which requires, in many cases, human expertise to actually decipher what is being seen. All of this is hugely, when you get into the detail of it, it's hugely complicated. But that's where the innovation can come in. So it's not just about quantum technologies and this innovation, but it's innovation in standardizing data. Then when you standardize it, you can then make that data accessible to third parties. You can then create new products and new services. So there's a lot going on, John, that we could talk about, and that's just around the world. That's just limiting to the world and close to it.
And so we've kind of had a little bit of history, a little bit of possibilities. Where are things right now? Where do you see things right now? What's the most exciting thing as of or in play at present?
Well, generally, or to do with quantum?
This is a family show.
Okay, so what I'm really excited about, I must say, is where we're headed. So it's I mean, you've had various announcements. One of them is ARKit. So you've got cryptographic keys. Okay, so we're starting to move the conversation on and trying to do something about encryption. We've been talking about it for a long time. Well, from my perspective, it's quite a long time, and we're starting to see implementations and seeing space and the natural expansion of humanity into space is something for me that is truly exciting. So one of the things that I went as a fanboy to NASA. For me, it was a dream come true, just to be there. I don't think they were aware of it. As far as I was concerned, I was there to talk about the UK program, UK quantum program. But I was like, wow, this is so amazing. So one of the things I talked about, and I want to try and get onto this. I want to push the discussion a bit more. Is the Lunar Gateway. So we have the International Space Station, and there's you can download an app and you can get a live stream from it, and you can see the sunrises and sunsets happening so many times a day, right? And there was a recent picture actually I shared with my family here in Mendoza, which was a view, a sidelong view of Chile and Argentina in profile. And it was an amazing photograph. When you see these things, you can't help but just be inspired by our world, inspired by humanity's ability to wonder about the world, and then to wander around the world, and then to wander off-world as well, okay? So when you have something like the Lunar Gateway, for those of you who don't know, the Lunar Gateway is another space station, but not around the world, around the moon. So it's not a base on the moon, it's orbiting the moon. And it can be configured in one of three different orbitals. And it's going to be maximized. Every surface you can attach a module to, and it's going to be maximized for science experiments and for industry as well. Now, bear in mind, we're going further away from the Earth. It's not a question of just ringing. In the UK, you have the AA. If your car breaks down, you make a telephone call. Somebody comes and fixes it. Either fixes it and you're on your way, or they take you to where you need to go. If they can't, and so you have to be self-sufficient more and more. And of course, there's going to be increasing traffic between the Earth and the station as more modules come on and other modules are taken away. So where is that taking us? So John, I want you to think about this, because it's going to take us to Mars. Okay, you're going to start to think about mining resources or using resources from other planets. But think about the practicalities, not just about getting there. Think about timing. So synchronizing timing across parts of the solar system. So you can synchronize communications. You can have delivery schedules. You can have a pipeline going to other worlds. And for that, you need better materials, better power sources, better atomic clocks. You need a phenomenal understanding of relativity and how humanity can operate in deep space. It's a kind of a game changer when you start to think about those things. Because where would you put these clocks? Because they've got to be stable and got to be accessible. And mind blown, right?
Yeah, and that's without thinking of all of the impacts of relativity on time and things like that. And I'm someone that I can, just with 2 or 3 time zones on one planet, I can make a hash of it. So I certainly don't envy the people running the calendars.
John, just this morning, I was reading about, it's not been peer reviewed, but I was reading about an experiment in which the difference in time in a cloud of 100,000 atoms, cold atoms, was measured in a space of 1 millimeter. So there was a time differential between the top of the cloud of atoms and the bottom of the cloud of atoms.
The clock technology is incredible how it's moving forward. I mean, until recently, I thought that cesium clocks were the most accurate we had, and it turns out that was terribly antiquated for those that have moved on since then. again, I think there's some peer reviews and things like that need to occur, but I was certainly convinced after speaking with some of the team working on it. So. There are some phenomenal challenges ahead, but also I think some incredible opportunities. Just in terms, as you mentioned, the resources, using resources for travel, for example, but actually spinning that round and thinking of the resources that potentially could be brought back. In longer term, having certain industries off-world to improve the environment we live in. They may be sort of second and third stage, but some of the potential benefits are staggering. I think with space like quantum, a lot of the future inspiration we have may not be visible to people at this present time. There'll be a lot of things unlooked for.
No, absolutely, but it's absolutely key, right? So, in order to get there, we need a quantum literate workforce. Okay, we need to be able to accelerate the benefits of discovery. So fundamental science is key. In fact, fundamentals, there's got to be more funding invested into fundamental science. But also, I think with a mindset, and not everyone will agree with me, but with a mindset of accelerating the discovery into some kind of benefit. And if you can get to a virtuous circle where those benefits then benefit people back on Earth, for example, then that would be absolutely fantastic. So I want to kind of, when I'm talking about literacy, so when we talk about those use cases, around optimization, around simulation and modeling and Earth observation data that I was going through, we did this with the, so this is a Quantum Pathfinder challenge again. We did this with business leaders, and they loved the event. Okay, there was this sort of, if I use, their thrusters were firing. They got engaged again. They were inspired. Okay, it wasn't their day to day. This was something new and exciting. But one MD looked, turned around and looked at me and said, "Well, this is really great," and I could feel the buck coming. But our engineers, they're highly literate, but our engineers won't be able to use quantum computers. So I looked at them and said, yes, they can. And they can program them in one day, and I'll prove it to you. So we did that. So after following that, we did a hackathon. So again, partnering with ESA, the Satellite Applications Cloud with Oxford University, with two companies, one called River Lane, Cambridge-based quantum software startup, and another one called dV/dt. That's an odd name. For those of you who understand calculus, dV by dt is acceleration. And those who understand the joke, I'll leave you to chuckle. So that's the name of the firm, but they're a machine learning kind of startup, and together they've provided a framework by which we had about 90 people attend. So these aren't the MDs, these aren't the C-suite levels, these are the real engineers on the ground. And by the end of the day, at the start of the day, they were nervous. Nobody understood quite where we were going, what would happen. But by the end of the day, over pizza and a beverage of your choice, everyone was smiling because they'd done it. They'd taken and I forgot to mention IBM Quantum as well. They were the partners for the hackathon. So it's this sort of taking, we talked earlier about taking the risk, trying it, finding out you can do it, growing, seeing the smiles, and it was a diverse audience. Remember, most sectors have a diversity problem, right? An inclusion problem, but we wanted to make this diverse as we possibly could. Now those people are going back into their jobs and saying, yes, we could do this. This is now possible rather than impossible. And that culture change is one of these sort of intangible benefits, but it shouldn't be underestimated or undervalued.
I think as well. So we've on one of our previous talks, you mentioned that quantum doesn't discriminate, so neither should we. Yeah. And that's something that we see so much goodwill and people really aiming for some fantastic goals. But I think space as well, it's something that inspires so many of us. I think that it's one of those things, it doesn't matter what your background, people are inspired by space, and that's not just necessarily modern culture. If you go back to civilizations over the years, there's something fundamental, a curiosity around it. And I think perhaps being able to harness that for social gains and social goals and that, inclusion and diversity and actually having the benefit of having more minds and more vantage points working on it, it's not only desirable but fundamental, and that gives us a real opportunity not to stifle ourselves. So hopefully those two things coming together can really sort of push that forward as well and become the square rather than the times of its parts.
No, yeah, that's right. That's right. And one of the things I want to in this sort of revolution, if you want to call it, I wanted to stick into people's minds about this idea of being multi-skilled. And that is increasingly important. You know, suppose you're operating the space environment, say it's the upstream part of that, where you're putting instrumentation or satellites and working on those, and you have a quantum background, for instance. Or conversely, you're a data scientist looking at or a startup saying, I'm going to tackle the shipping problem using space data, and you're looking at a specific use case within that that has value, and you have a staff that can use quantum computing as well as AI and other things, and that is a multiplier effect that helps to accelerate everyone, not just business growth, but individuals too. And I think that's really important. So one of the things that I love about the quantum communities is openness and willingness to share, exchange ideas, and try stuff.
And I think it always gets to sort of this stage of the talk, and I feel like I've been a bit selfish, sort of keeping the guests to ourselves. So it would be good, if it's okay with you, Roots, to maybe open out to some of the audience. And there's been an awful lot of activity in the chat, which shamelessly I've not been able to keep up with entirely, but I have noticed quite a few comments from Alexandra Zagostin, Bill Gonzalez and Paul Grimm. So if any of you would like to sort of take the mic, and if you have any questions, please join in.
Or observations. You don't have to have any questions. If you just want to say something, say something. It'd be great to hear from you.
Well, if I may, thank you very much for your invitation. I would like just to stress that at the moment, it would be more wise to concentrate on hybrid and analog quantum devices. We simply do not have the technology yet necessary to provide all the overhead for digital universal gate-based quantum computing. And we have very much impact from computer scientists who simply forgot that right now conventional computers are so powerful that you can forget that everything is based on some physical processes. If you could borrow some people from 1940s who understood that you have very limited memory and half of your memory banks will burn out in the process of computation, we would have a more realistic approach to our quantum devices. So this is why I think optimization and analog quantum devices application to real-life problems will be crucial if we ever develop full-scale quantum technologies. We need quantum engineering, so to speak, more than, say, quantum computer science at the moment.
I think, Alexander, that's a really, really great point. Quantum engineering is absolutely key. Just so you know, I'm hoping it'll be published. I don't know if it'll be published this year, but one of my last contributions for the UK hub was to write an accessible, well, I hope it's more accessible, report on analog quantum simulation and its importance. So I haven't forgotten about it, but we need these hybrid schemes as you talk about, with all these tools that we can harness.
Yeah, I'll add, this is Bill Gonzalez. I mean, I'm doing a lot of research and taking several courses, and yeah, the hybrid is the way to go, at least for now. What we're seeing is advancements being made on the quantum side, at least in regards to the way things are done, is adding improvement to standard classical methodologies for solving problems. And so sometimes, the simulation of quantum systems is also beneficial. A lot of what we initially study on is simulators, not necessarily true quantum machines, although we do get to do some advanced calculations on some of IBM's hardware and some of the other providers. And there is a lot of hype. A lot of people are now starting to bring that up and saying, it's a lot of money being thrown in. A lot of universities are starting to look that way. A lot of people are taking training, and it's a hard nut to crack. It's very hard to understand, but I think people are at least trying to lay some groundwork and try to learn enough about it to see if other people can contribute. But on the hardware side, yeah, I mean, there's several modalities that are being utilized: trapped ion, superconducting. You've got some people using fermions or Majorana type technologies, or at least concepts. And I'm still waiting to see which one's going to be the most solid one to land. But we have local researchers here, for instance, in Texas, that are working on trapped ion. You've got even the companies like D-Wave, who are mainly using annealing technologies, who are now talking about using standard or more acceptable type of hardware, quantum hardware. But yeah, noise is the biggest issue. Everybody's trying to combat that. People are trying to figure out ways to resolve error correction. And so I just wonder, with all the money going in, whether we'll see a much more quick advancement than other technologies that have been studied in the past. I'm waiting in the wings, trying to see what's going to come of it. Thank you. Thanks for everyone's conversations as well too. They're very lively.
So thank you, Bill. It's quantum computing is early. I keep telling that. It is advancing though, and these advancements that are being made are important. The question is when we will get to value, and then who defines that. So value in a research context is a paper, for example. Value to a business, has it saved any money or made money? That's a harder question to answer. But we're seeing so my focus has been developing the ecosystem in the UK, and now trying to do the same here in Argentina. But you make an ecosystem brick by brick, and you have to be authentic. You have to be truthful. You have to try and see things in perspective, and that's getting harder and harder. There's a lot more noise, not just in quantum computers, but just made by people.
Yeah, and I think with all of these things, it does. There is that sort of dichotomy between the technology and the people, how things are implemented, and then they can't be separated. So then obviously that's tied to the finance, the business models, the investment models, and what that looks like. So I think, as with most things in quantum, there's almost more unknowns than knowns. There's a rough prediction, but quite how that manifests itself is unclear. And I've just noticed, Chris, you've unmiked yourself, so come on in.
Yeah, so I have a question. As a non-physicist, Roop, I'd love to get your take, and also Bill and Alexandra. But do you think one of the qubit solutions will work better in space applications? I sort of posted in the chat that space on some level is an ideal environment because it's a vacuum and it's cold. But as I think Alexandra pointed out, there's cosmic rays and there's space junk and other. But I mean, so if you were doing sort of room temperature qubits in space, you'd have to heat them up somehow, right? Or just what your take is on the sort of whole portfolio of options.
So okay, let me go first. But what I think is this: if you ask me to put some money on something, You know how hard it is for me to open my wallet, Chris. So, so what I would say is this: already you have a space-based quantum system because there's cold atom laboratories there. Okay, and you have companies like Cold Quanta who have this ambition to put more quantum technologies like that into space. Whether that's computation or not is something else.
Mm-hmm. Yeah.
Okay, and so there is already one type of candidate technology already there, but it's not a computer. But you could sort of kind of see it could be.
Yeah, that's
right?
great. Yeah.
But it needs cooling. So you've got to find out lifetime because you need dilution fridge of some kind up there. The second dilution fridge or lasers and power. Another one is I would say is photonics, because if you have a chip-based system and photons of light, then you can conceivably have a space qualified material or chip. And then you could start to do quite a lot of interesting things, because then you can say, for example, if you had, I don't know, a dozen satellites around the Earth that were entangled with one another, you didn't just have a computation resource, you had another resource that could do far more interesting experiments and fundamental ones too.
Yeah. Well, it seems like, again, I mean, so superconducting requires, lots of apparatus and technology, and certainly getting stuff up into space and then maintaining it, is very expensive, right? So it seemed like you want to go with the most efficient from a scalability and technology complexity perspective that you could. I mean, my thought is nitrogen vacancy, is that like, because they're making these rack mounted devices, right? Quantum brilliance. Is that something that might work better in space, just because it's small and easy to get up there? And
we have to be careful, because when we're talking about these things, we're just shifting where the cooling is. Okay.
Yeah.
So yes, ND centers don't, but you might need detectors that require cooling of some kind.
I was just thinking that, it'd be interesting to find out of the different modalities, because we've got a list of them, of course, that are out there. Is, how many companies are concentrating on each one of them would sort of give you an idea of where everybody's putting their money, and whether it is spread across. But the other thing is, I would imagine that maybe there's some thought regarding, taking these systems up in space, but I would imagine that they're probably just struggling with trying to get them to work here on Earth with all the disturbances that we have, even just in general terms. I like the idea of underground. I don't know, how much thought has been put into that, because I know there's some facilities where they've got some basic features of the facility that prevents or filters out a lot of the cosmic radiation and all these other things that are flying around. But you wonder, I think we're still a far way off. Not even, room temperature, of course, is probably within, the near future, which would be what you would need to, really, I think, make something that would be usable, in a more wide area. Over.
I mean, I would guess it's NASA and the European Space Agency, and certainly China are investigating, what will work up there. And
the China's doing communication, right? Of course, straight up, using entanglement and some other types of methodologies, but it's not actually quantum computing or hardware that's going up there. I think it's basically just some type of communication system using lasers, right? From what I understand.
Yeah, that's right. Yeah. They had back in the 2019 conference with NASA, there was a presentation from Austria. So China and Austria had signed an agreement that whoever got to space first could use a result. And China got there first with the Messier satellite. So they had a 6-second data burst.
Wow.
Which the Austrian university had to pick up. So they had a time window of 6 seconds to pick up the data to verify entanglement and everything else from the photon resources that were on the Messier satellite.
Huh.
So can you imagine? You're spending a fortune on equipment. You're getting a time window, and you need the pickup array to pick up the laser communications, and then you get the data dump, and you have to do everything within 6 seconds. It's extraordinary.
Yeah. Oh my goodness. Thank you, Rupesh. That was great.
And just coming
Thanks, Chris.
Just coming back to Bill's point, actually, Michel Kurek created, it's about 6 months old, but he created a graph showing the different players within each hardware technology. I mean, 6 months is a long time in quantum, so it probably needs updating significantly now, but it was certainly an interesting article. That there's like a circular diagram with all the players, whether it's NV, ion trapping, superconducting, and all of those different modalities. So I was trying to find it during the chat, but I'm not quite good enough at multitasking.
Hey, John, if you could put that
I'll
link,
look around for it.
John, can I just make a comment on NV centers? There is a laser milling kind of technology developed by Oxford University and Element 6, the diamond company. And they can implant NV centers anywhere you like. So for example, they did a bit of fun and at different depths within a diamond crystal. And for fun, in one of the quantum technology showcases, one of the researchers drew the letters NQIT, NQIT, which was the name of the first quantum computing hub in the UK. That is also exploring NV centers as one of the modalities. So this was exciting to see, because of course you need ideally millions of them. But there is, that technology is there. It's been proven, but it now has to be matured of creating NV centers at will anywhere you like within a diamond crystal.
Wow.
Hello, if I could just make a few comments. If
Hi,
you can
Paul.
hear me.
Yes, please carry on.
Hi.
Yes.
My head is exploding. I love this session. I've got so many things to talk about, but I know we're limited in time. So maybe, John, you can have another session sometime. Going to Mars, Mars has helium. I'm sorry, the moon has helium-3. That's our next energy source. We're going to be going to the moon like crazy with bulldozers and lifters and returning material, but it's only good for fusion, not fission. So it's not radioactive. Anyway, I want to put that down for a minute. Landing on the moon is very easy compared to 240,000 miles. I drive my car further than that in 6 years. But going to Mars, we need a way station. There's something called geosynchronous orbits. And if you're not in a geo area, you then may have to hold the space station by boosting it often or occasionally. But a trip of 6 months to Mars is quite long. That's why these people go up to the space station for 6 months or a year at a time to see how they fare. If they could build a way station that you travel 3 months, of course, if you boost the speed, the problem with speed is you can't slow down. In order to slow down, you have to reverse the rockets and then use fuel to do that, and they can't do that yet. The other thing, I worked for IBM for 25 years. I worked for Lockheed Martin for 15 years. I was in Royal Space for 2 years. So I have 7 years of AI, 3 years of quantum, and I'm retired. I'm here doing nothing. So I'm ready to solve problems. Yeah, I am bored. So that's why I've been learning quantum on my own. Yeah, the speed of the Earth, the navigation, navigation back to the Earth. The Earth travels around the sun. The sun is 93 million miles. You guys write this down. The sun is 93 million miles. So 2 times ours, 186 million diameter, distance around, circumference about 600 million, just under 600 million. Take 600 million divided by 365, you'll get millions of miles per day. Take that number and divide it by 24, you'll get millions of miles per hour and so on. Divide by 60, you'll get millions of miles per minute. Divide by 60 again, you'll get millions of miles per second. Now, why do I want to use second? I want to use second because I want to compare it to a 30-06 rifle bullet. If you take that number that I just broke down and divide it 2,800 feet per second, you're going to get a number something like 30 times. So the Earth is traveling 30 times the speed of a bullet as you and I are sitting here talking to each other using this technology. So the point is, you got to get back to the Earth. And that takes navigation system. While this Earth is moving 30 times the speed of a bullet, or do your own calculations, see what you come up with. So, you know, anyway, getting back to the way station, whatever that would entail. Now, I haven't talked much about quantum yet, but I'm working on a couple of programs with quantum, but I haven't done actually programming. I do the Fourier transform. I think I demoed it to John and a few people that he invited. But I have some demos I can show you guys that has to do with rotating and has to do with quantum waveforms. They're amazing. I mean, they're phenomenal for people who are trying to learn quantum and see what that's all about. I have some key things that will help you turn the light on. Anyway, I'll stop here and let someone else speak, but I'd love to come back again, talk about space. I lived in Washington, D.C. for 60 years. So I went to the Space Museum and I worked with the White House. I was invited to the embassies. I worked on the air traffic control system for Heathrow Airport, John. So if any of you have flown into Heathrow, you probably use some of my work.
Hey, Paul, so bravo and thanks. Could you put any links to your content or work products or writings in the chat, please, just so we can share with the assembled throng here?
Absolutely. They are on my profile. If you look at my LinkedIn profile, and you'll see some of the demos there. I did them quite a while ago, but I have some new ones and you can pick them up there. But yes, I can share it.
Great. Thank you very much. Yeah. I'll learn more about what you're doing for sure.
Okay.
I think from our
Thank you, Paul. That's phenomenal.
I think from our conversation the other week, it's nice for the boot to be on the other foot and your brain to be exploding rather than last time. I think our minds are all blown, so it's nice to be able to repay the favour. And we are so that the space theme is running until the end of November, so plenty more to come on that side. But Rupes, it would be good to get your reaction to Paul's comments as well.
Oh, Paul is amazing. And first of all, I'm disappointed I wasn't invited.
Me too.
To see some of these demos. Yeah, you, Chris and I, why were we excluded? Exactly.
I don't know. We didn't make the cut.
Exactly. We didn't make the cut, Chris. I don't know why.
I don't know what happened, but
we were prepping.
John has a calendaring issue, to be honest. He needs counseling on his calendaring skills.
But this is it. This is what is really exciting, because when we're talking about quantum, we're talking about how the universe operates. We're talking about what a way to put it. Earth is moving 30 times faster than a bullet. Now, I grew up with Superman, right? Superman comics, faster than a speeding bullet. And I had no idea when I was a kid, okay, growing up, that the Earth was moving faster than Superman. There you go. And what I want to sort of leave this session on is just a more of an upbeat note, is to see how we can harness all of these wonderful creative ideas, the engineering know-how, and the applications of all of this for the betterment of our world, for the betterment of humanity, and for the betterment of other worlds. Because are we going to turn them into trash heaps too? This is a really important question. How are we going to behave up in space? and given our behaviors down here. And so this is something I think we need to bear in mind and be serious about. Because if we can solve our sustainability, our climate problems here, we won't create such big messes, rubbish tips and other things elsewhere.
I would like to
You know,
make
we don't want
quick-
to. Please,
quick
Paul,
comment.
carry on.
Sorry, I'd like to make a quick comment on cleaning things up and building from rubble.
Yep.
There's a movie called Chocolate. I recommend everyone to see that movie. It has 3 or 4 different levels, family, building, and anyway, it's a wonderful movie. It's called Chocolate.
Can you put that in the
Could you
chat,
put the
Paul?
name? Yeah.
Put the name in the chat. I've never heard of it, but on your recommendation, I'll track it down.
Oh, I think I sent it to Alexander.
Yeah, you got to pop up the everyone drop down, right? Yeah.
Yep.
Easy to do for sure. Chocolate, really? Okay. How old is it, Paul? Is it recent or?
Yeah.
It's about 10, 12, 14 years old.
Wow, okay.
Okay, great.
Hey, Roop, one last thing again, you know me, I'm the link in the chat guy. So is there any documentation of like the work that you did or the meeting in the US or that you could point us to? I'd love to read more about.
Yeah, the thing is there is, but it's not sort of publicly available. It went into a government strategy document.
Right, okay. Never mind.
We can tell you, but
Yeah, you could tell me, but you'd have to kill me. Really.
And lose one of my best buddies? I don't think so. But
I need level 3 clearance to be able to read it.
exactly. But I'm happy to write one.
Okay. Yeah, I'd love
Let's put it
to.
that way.
Yeah. Just maybe write a piece about that work with any details you
Yeah.
can share without having you
Sure.
arrested in Argentina.
You're non-extradition still? Depends who you know.
Exactly.
Um,
I don't have level 3 clearance, John. So not yet.
Not yet, really.
and whilst we've got such luminaries on the talk, is there anyone else that would like to come and join and add anything to the discussion? It's a great opportunity for any of you out there.
Yeah, don't be shy, right? I just say, Emma Ford, thanks for your kind words in the chat.
I'd like to make one more comment about landing on Mars. I think the solution to landing on Mars is small, like a one-man rocket. Easy. I can guarantee you there will be no failures with one-man rocket. They can take from orbit, drop person by person down to the surface. Of course, they could preload the surface with other things for survival. But trying to land these huge ships on, that worries me to death. That it's very risky to do that. So I favor the small. The COVID-19 is small. It's taken over the world. Windmills, we can generate windmills that are this big, generate milliwatts, put them in a bank, and you can take the slightest breeze and generate electricity. It's a multiplicity. It's in the numbers. Okay, thank you. Great presentation. I appreciate everyone. Thank you.
Thanks, Paul. So Rupesh, have you got any closing comments for everyone? It's been quite a stimulating discussion with lots of unexpected twists and turns. So
yeah, so I want to get practical. I want to get practical and encourage people exploring quantum technologies, including quantum computing, and start to look at use cases. Start to look at ways we can space qualify different products, different pieces of equipment, and start to accelerate all of this and see where the side innovations are coming from. So where they can be applied back on Earth, where other innovations could happen as a result. So let's talk to one another. Let's come together as a community. Let's start working on different projects, whether it's advancing quantum machine learning / AI with space-based data, whether we can help clean up space faster, what technologies could enable us to live sustainably off-world, and whether that's in an orbiting platform or whether it's a base somewhere. And so these are real. All of these things aren't trivial. But let's start getting going. Let's connect and start working on things, because at least putting in the groundwork, even if the technology is not here today, but it may be here one day, right?
Yeah, here, and I think sustainability and integration or interaction absolutely essential if these things are going to become a success, or anything as close to the success they could be. So here, totally agree. And
I just want to make one thing as well, because we've heard a lot about hybrid. So hybrid is generally classical with quantum. So classical systems doing kind of heavy lifting, quantum processes working on very specific parts of the problem. Okay, the quantum part of the problem, feeding back into the classical, which then feeds back into the quantum, and so on, right? But I want to talk about hybrid in a different way as well. Hybrid, in the sense of you have a problem that you want to solve. Say, how do you optimize the Mars mission? And then you use different technologies, perhaps I'm just viewing them in a network. Whether it's annealing technologies, whether it's supercomputers, whether it's AI, whether it's neuromorphic, whether it's quantum computers, analog simulators, on the relevant parts of the problem, and then bring it all together to give to help with the solution. So we work in a collaborative way with all of these different technologies at the right point. So, and with that, I'm going to give my salute and sign off from, sadly, from this world. It'll be wonderful. One of these days, John, you have to get a pass either from Richard Branson or Bezos and do one of these things from orbit. That'll be fantastic.
That's an idea. Yeah, entangled discussions from low orbits.
Exactly. It'll be much shorter. Probably be about 11 minutes. But
yeah.
the value would be.
At least I'd have an excuse for not looking the right way at the camera, or my mic turning off, or something like that.
You'll be floating around.
You'll be whoa.
Oh, look, John's over there.
I've just seen Alexandra put his hand up as well, so please.
Sorry, actually, I wanted to applaud.
Oh, I'm sorry. I think
Thanks,
you have
Alexandra.
that was
Very good workshop.
Thank you.
So I want to applaud everyone as well. I want to thank everyone who joined, everyone who's watching this post live. And thank you, John, as well, for inviting me. And it's been a lot of fun. Really enjoyed it.
And Rubes, thanks once again for being the guest on this series, and thanks to the audience for both joining us and also participating and really stimulating the discussion as well. So wow, what a way to restart, and I certainly think that is back with a big bang. So thanks everyone that's attended today, and also is attending or is watching on YouTube or LinkedIn. I can see lots of people promoting their books in their screen, so please put the links in the chat box. We don't mind a little bit of self-promotion on this channel. And so we're back at the same time next week, and we've got a real rising star of the quantum space arena, Manuel Ntumba, and he discusses how quantum technologies support sustainable geospatial applications. And I'm glad I said that without slipping any of the S's. So, so we'll see you next week at the same time, and I'm going to work on my pronunciation on that. So hopefully it goes well if I've got to repeat it a few times. So thanks everyone for attending. It's been a real pleasure, and see you all next week.